Right, so the periodic table. Let's go over the things that we need to understand about the periodic table. First thing is we know there's this staircase that separates the metals from the non-metals. How do we know where the staircase is? Well, you just find a metal around about here, which we know is a metal, and aluminium is a metal. And then we want to find a place: is silicon a metal, or is boron a metal? Hopefully you know that at least one of those is not a metal. And if you do, then you know that the staircase must start there, or maybe you can say it's there. Either way, we can then draw the rest of it. So it's just about finding any part of the staircase where we can say, I know that this is a metal, that's not a metal. Usually people haven't heard of all these other substances, but they should know that aluminium is a metal. So aluminium is a good place to start. So what else do we want to? Well, what is a metal anyway? A metal is an element that tends to be on the left. Now we will actually look at each part of this periodic table. So I'm going to just highlight the different parts. So this part, which I'm going to highlight in yellow, are the transition metals. They're very weird, but we won't look at them yet. In general, we'll say that the metals on the left, the non-metals are on the right, and so they have low group numbers, and non-metals have high group numbers. So, can either of you tell me what do group numbers? What does the group number tell you about an element? Yeah, so the group is the number of electrons in the outer shell. Now, we don't actually have to memorize that so much because we can discover it for ourselves. So, for example, if I took lithium and I see that well, let's look at another part of it. Let's look at one of these substances. I'm going to take beryllium because I've got a bit more space to annotate this. So this number here is called the mass number. You can also call it the atomic mass number or the relative atomic mass, but it's always going to have the word mass in it. Okay, and this number here is the atomic number. And the reason why it's called the atomic number is because it just means like atom number 1, atom number 2. So this is the first atom, this is the second atom, this is the third atom, and this is the fourth atom. Now, what is it that differentiates one element from another? The only thing that changes one element from another is the amount of protons. Now, we know that atoms are made out of protons, neutrons, and electrons, but you actually can have different versions of the same element that have different numbers of neutrons. So, for example, carbon will always have an atomic number of 6, but it could have a different mass number. And so basically the atomic number tells you the number of protons. So all carbon atoms have 6 protons. If they didn't have 6 protons, they would not be carbon. The mass number is the protons and the neutrons added together. So if this carbon 11, for example, has 6 protons, then it must have 5 neutrons, because the neutrons and the protons added together have to add up to 11. So these are all isotopes of carbon. And you can see that they all have the same number of protons. So what else can we say then? Well, if we have how can we work out the number of electrons then from this? Well, the electrons are always the same amount as the protons, for neutral atoms. So if we take our beryllium atom again, it's going to have 4 protons, and then I'm just going to ask you how many neutrons. Okay, so yes, 5 neutrons in the beryllium atom. So what I'm going to do, in fact, I'm just going to not bother with drawing the nucleus. I'm just going to write Be in the middle, and then I'm going to draw a circle around it, and I'm going to draw the electrons. Now we've got, if it's neutral, then it's got 4 protons. It's going to have 4 electrons to balance it out. The first shell can only hold 2 electrons. So once I've filled that first shell, then I needed to do another shell. The second shell can hold up to 8, but I only need to do 4 in total, so I need to do 2 more. So 1, 2. So that's my beryllium atom drawn, and I don't need to know where it is in the periodic table. I just need to know this number here, and I can draw my beryllium atom. However, now that we've looked at our beryllium atom, we can see that there are 2 in the outer shell. And that will be the case whenever you draw any atom in group 2. And any atom in group 1 will have 1 electron in the outer shell. You can write out the order of these electrons by just doing this. So this means how many in the first shell, how many in the second shell. And we call this we might call it the electron structure, or the electron configuration. So if in the exam they ask you to describe or state the electron structure, or the electron configuration, or the electron arrangement, but they don't give you anything they just give you one line, then that's what they're looking for. They're looking for this kind of thing. Whereas if they give you a lot of space and then make it a bit clearer, they might want you to draw a diagram. Okay, so what else can we say about beryllium? Beryllium's also got 2 shells. That is because it's in the second period. The period is the row, and the group is the column. So the period is the row, and the column. Let's rewrite that. The column is the group. So a while ago I was talking about how weird the transition metals are. We're going to gradually get to that, but we can start to see one thing weird about it is that it doesn't seem to have a group number. We've got group 1, group 2, and suddenly nothing, and then group 3. So transition metals don't seem to have a group number. Let's try to understand why that is. Well, if I look at beryllium again, when beryllium forms an ion, what it does is it loses 2 electrons, and it becomes therefore it has a positive charge, 2 plus charge, and then the electrons are now free to do whatever they want to do somewhere else. So this is and the reason why it forms a double positive charge is because it now has 2 less electrons, and before it had the equal number of electrons and protons, so it's lost some of the electrons. So the beryllium ion will lose that outside shell and just have the inner shell and this double positive charge. The reason why it loses these outside electrons is because what it's trying to do is form a full outer shell. So what were its options? It could have filled this second shell by adding 6 more electrons, but it's a lot easier to lose 2 electrons than it is to gain 6. And that's going to be the case for all metals, in fact. So we should write a few notes here. So just to differentiate between metals and non-metals. So metals metals lose electrons, form positive ions, and have a small number of electrons in the outer shell. Now all those things are connected, right? They lose electrons because it's easier to gain than gaining them, because there's only a small number to lose. They form positive ions because they lose electrons, because when you lose electrons you're going to form a positive charge. So, and obviously non-metals do the opposite. Okay, non-metals have a more full electron shell. Those are a little bit weird. Like boron only has 3, so it's a bit weird. Why would that one gain electrons? So there's more to the story, but we don't need to know about that. However, it's still true that non-metals gain electrons, form positive ions, and they have a larger number of electrons in the outer shell. Okay, so group 1 have 1 electron in the outer shell, so it's going to lose 1 electron. Group 2 have 2 electrons in the outer shell, and so it's going to gain 2 electrons. Lose 2 electrons. So group 1 metals will form +1 ions. Group 2 metals will form +2 ions. And group 3 metals will form +3 ions, apart from boron. Group 3 metals will form +3 ions. So what about the transition metals? They form more than one type of ion. Okay, so transition metals can form multiple types of ions. Okay, that's what makes transition metals weird. Another thing that's interesting about transition metals, and one of the things they'd like you to know, is that the compounds they form are different, are colourful. So copper sulfate, you might, if I get a picture of copper sulfate, where is it? Let's get a picture of it. You may remember that copper sulfate is bright blue. So I'll get a picture of it. Copper sulfate is bright blue, and let's copy an image there. And then we got iron oxide. Well, iron oxide is rust. So what colour is rust? Rust is bright red. Okay. So transition metals are colourful. Transition metal compounds are colourful. Non-transition metal compounds are not. They're usually just white. Okay, what else is there to say? Well, group 0, what does that mean? It has 0 electrons in the outer shell? No, of course not. That wouldn't make any sense. Well, it's kind of true. If it has 0 in the outer shell, then that isn't an outer shell because it's empty. So, but basically, group 0, otherwise known as the noble gases, they have a full outer shell. Okay, so all of these, and if you draw them out, like look at the first one, 2 electrons in the outer shell, 2 electrons in altogether, and they would both fill the first shell. So therefore, the first shell is now full. So all of these have full outer shells. The other thing, I guess, to include then before I just wrap up this video is group 1 are the most reactive metals, and group 7 are the most reactive non-metals. And that's because group 1 only need to lose 1 electron, whereas group 7 only need to gain 1 electron. So if it's easier to do that, if it's easier to either form the ion, it's going to make it. It's going to be very reactive. So yeah, I'll wrap up the video there and put it around about there. Okay.